Good afternoon. Now I want to discuss this relationship between electric potential and electric field. And the main question I really want to get at in this video is whether Mathematica can do a good job of turning an electric potential diagram into a vector field map. So let's start with the electric potential from a positive point charge. Generally, it looks like this. K sub E is called Coulomb's constant. It is 8.99 times 10 to the 9th, and that is in, well, we can see from the equation below that it has to be in volt meters per coulomb, but that's not a great unit to use. I think it's usually given in Newton meters squared per coulomb squared, which makes it very similar to the universal gravitational constant of Newton meters squared per kilogram squared. We can set the central charge to whatever we want because I just kind of want to get an idea. We could set it to be a single proton and be 1.6 times 10 to the times, whoops, can't get it right, 10 to the negative 19th coulombs. And then let's just see a plot of this thing. We'll do plot 3D. Plot 3D. There. I've heard rumors that there's a way to get the application to fill this all in for you, but for now, I'm just going to do it the old-fashioned way by typing. I'm going to put in, say, negative 5, 5, and y going from negative 5, comma 5, and see if that actually pops up anything. Okay, it won't because we haven't defined what r is. I could have stopped it, I think, by pressing Alt period, but yeah, that's not coming up with anything meaningful because I have not defined what I mean by r. R is a function of x and y, and it is equal to the square root of x squared plus y squared. So I will go ahead and make that a function of xy and see if that comes up with anything. No, it seems to have a disagreement with me calling this k sub e. So let's go ahead and change that to just plain k e without any subscript and see if that fixes it. No, perhaps the problem is that it's not getting a good machine-size real number in this region. So I'm going to change the value of the charge so that k sub e times q comes out to be equal to 1. So this will actually just be 1 divided by square root of x squared plus y squared. And that actually comes out looking pretty nice. Looks like a little volcano. Okay, now that I've got the electrical potential graphed, I want to see if I can show the electric field. The electric field is going to be in the form of arrows coming down the mountain, but it's going to be viewed in 2 dimensions, so the arrows will just come out radially from the center. The big question is whether I can find a way to get Mathematica to show me those arrows. And I have 2 secret weapons at my disposal that may help. One of those weapons is that I know that the electric field is something actually called the gradient of the electric field, of the electric potential. The other is that I know Mathematica has a function called VectorPlot that is designed to plot vector fields. The gradient is called a vector differential operator. It's usually expressed, it is usually expressed with the symbol Nabla, which is not a Greek letter, but it resembles the Greek capital delta. It's upside down though. Anyway, Nabla is equal to a vector, an incomplete vector. It's kind of del x, del y, del z. It takes the derivative of something, some function that might be, for instance, v of x comma y comma z, and becomes a vector being del v del x in the x direction, del v del y in the y direction, and del v del z in the z direction. And so it gives you the slope of the x direction pointing in the x direction, the slope in the y direction pointing in the y direction, and the slope in the z direction pointing in the z direction. So what happens to our potential? Remember, our potential is v of x comma y comma z is equal to k sub eq, which is constant, times 1 over r. And that is k sub eq divided by the square root of x squared plus y squared plus z squared. Now, if you don't know how to do a derivative, what I'm about to do probably won't make much sense to you, but you might understand the algebra of taking this and writing it equivalently as k sub eq times x squared plus y squared plus z squared to the negative 1/2, because that is the square root written up, the reciprocal square root written on the bottom. And I'm going to take that first with derivative with respect to x. And what happens then, when we take a derivative, we multiply by that exponent. So we'll have negative 1/2 k sub eq times x squared plus y squared plus z squared times to the power of negative 3/2. And then, I believe this is called the chain rule. We took the derivative of the outside function. Now we have to take the derivative of the inside function. And the derivative of x squared with respect to x is 2x. The derivative of y squared is 0. The derivative of z squared with respect to x is 0. And so our final answer, these 2's cancel, and we end up with k sub eq over square root of x squared plus y squared plus z squared cubed times x. Now you can show pretty easily from that del v del x comma del v del y comma del v del z is going to equal the vector k sub eq x over square root of x squared plus y squared plus z squared cubed, k sub eq y over x squared plus y squared plus z squared cubed, comma k sub eq z over square root of x squared plus y squared plus z squared cubed. And you can simplify that by writing this is k sub eq over square root of x squared plus y squared plus z squared cubed times x comma y comma z. You can simplify it even further by saying it is k sub eq vector r divided by r cubed, because the square root of x squared plus y squared plus z squared is r, and we cubed it. Now that's not the familiar form of the electric field that from a point source is generally written as the magnitude of it is usually written k sub eq over r squared. And that kind of is derivable from this, because if we take the magnitude of this thing, where the r over r vector is just going to be the unit vector in the r direction, which is sometimes written with a little hat on it. So in Mathematica, we only want to use a two-dimensional plot. We could essentially imagine just setting z equal to 0 and imagining what would appear in the plane. Now I'll tell you, I was hoping to hit the pause button and show you exactly what I was going to do on the first try, but I have not had success yet. I have managed to do vector plot of x comma y. It shows that if if you have a vector field that just says x comma y, then the bigger x is and the bigger y is, the bigger the vector is. On the other hand, if you just have a vector that goes x comma y, this would be the vector x comma y over r, which is actually the vector r over the magnitude of r. And you can see that the vectors are the same size everywhere. Now this is not what you couldn't get this image from the electric field lines as described in our textbook. This would be a rather strange thing where you have diverging charges, but somehow they're also the same density as you go out. So somehow there'd have to be extra charges coming from or extra electric fields kind of coming out to replace the ones that were leaving. But we didn't have just a single square root of x squared plus y squared on the bottom. We had a cubed. And there seems to be something malfunctioning, because when I put a squared in there, all we get are little bitty dots. When I put a cubed in there, wait, that's not. When I get a cubed in there, all Mathematica is showing me is one single little arrow. Sometimes when things aren't showing up, it's helpful to look into the options. Things that might help is performance goal. Let's go with performance goal of quality. Okay, still doesn't look like very high quality to me. But I did have an idea of what's going wrong. Right here, in the center of this particular vector should be right next to 0, and that is where this will be divided by 0. So somehow it is putting this vector in as very, very big, and then everything else looks very, very small compared to it. So here's a region function. Let's see if we can get that to happen. In this example, they're doing an xy less than 0, which puts it in this quadrant and this quadrant. I want to try to get a region with x outside of a certain circle. So I thought maybe I could just say x squared plus y squared is greater than 1, but that didn't do anything. Okay, so I replaced VectorPlot with StreamPlot. StreamPlot only tells you the direction, not the doesn't attempt to try to tell you the magnitude. It looks like my region function actually did do its work. Let's see if this changes. If I change that to 0.2, if that changes anything. Yeah, it made the region inside there a little bit smaller. But the key is the magnitude of this thing is supposed to be tied to the distance. It should drop off with the inverse square of the distance. And thinking of it in those terms made me think of another command called StreamDensityPlot, which what it does is it plots the streamlines for a vector field with a background based on field magnitude. So it doesn't try to use the density of the field lines as its magnitude. Rather, it tries to use the density of the field lines themselves as the magnitude. Unfortunately, all of the magnitude field lines in these regions is considered by this program to be approximately 0. So they end up being exactly the same density. They have options in here to use the logarithm of the field magnitude instead, but I'm not sure if I want to spend the time on that right now. Alright, I'm going to have to wrap this video up for now, but I do want to, maybe in the next video, if I have time, put together a like the potential field from a positive charge coupled with a negative charge, and then see if I can get the StreamPlot or the StreamDensityPlot from that figure after finding the gradient that you would get out of that electric field, and see how Mathematica does at creating a somewhat more interesting gradient plot with more than one charge involved. So I'll do that coming up in a few minutes, or later tonight or tomorrow morning. But for now,